Good day, greetings. We're going to look at our physical sciences chemistry paper 2. Duration is 2 hours and the marks is 100 marks. Then the first page there we have got our instructions, then proceeding to the first question, which is our multiple choice question. So now we're going to go through our multiple choice questions. So the first one reads, the process when a solid substance, so we're having a solid substance, changes directly to a gaseous phase is called, right? So these are processes. Now we know there is a state change there. So the first one they were given is evaporation, right? So we need to know what evaporation is. So this, in terms of the state of the change there, the state changes from liquid to gas. So here we're having a liquid to a gas, right? So this is a liquid to a gas, but here we're told in terms of a solid to gas. So the second one there says condensation. Then condensation here is gas to a liquid. So the change of state is gas to liquid there. Then sublimation is when you automatically change from solid to a gas. So it means our correct answer there is going to be option C. Then moving on to the next option. Next question, it says which one of the following substances is a pure substance, right? So which one of the following is a pure substance? For us to be able to answer this one, we need to know what a pure substance is. So by definition, we know a pure substance is consists of one type of matter and cannot be separated into simpler pieces by physical means, right? So according to this here, this one we can break down our steel into simpler pieces, and then we also have our sulfur. So our sulfur there is the correct option, which is a pure substance, right? So the juice there, it contains too many ingredients. Here we're having our salt and our water, and again there it's not a pure substance. Then we are going to move on to 1.3, which reads 1.3, which one of the following represents the electronic configuration of phosphorus? So we're looking at the electronic configuration of what? Of phosphorus, right? For us to be able to answer this one, what we are supposed to do is to go ahead and check our periodic table, and then there we're going to find our P, right? So there, this is what you're having there, which is a 20 there. So it's P 15 there, sorry, 15. So this is the phosphorus that you're looking for. So it means here what you're having there is going to be a total number of 15 electrons, right? So if we're having this one now in terms of our SP notation, it means all these numbers should add up to 15, right? So it means we're going to start with the 1s2, then 2s2, then after that you're going to proceed to 2p6, right? So if we are to check the number of electrons that we have used here, we've used 4 plus 6, which is equivalent to total of 10, right? So remember we said this one has got a electron number of electrons is going to be what the atomic number that is given is 15, so we're expecting 15 electrons there. So it means here we're having 10. After 2p6, then we're going to proceed to 3s, right? So 3s2. So it means now we're having a total of 2, which is 12 now. We're having a total of 12. Then now we're trying to approach 15. Then after that is going to be a p orbital again, which is 3p6. So this is the electronic configuration that we are looking for in terms of our phosphorus. So if we are to look at this, option B is the correct one there. So if we can add all these numbers, 2 plus 2 is 4, plus 6 there is going to get a value of 10, plus 2 is equivalent to 12, then plus 3 is going to be 15. So this is the correct electronic configuration of what? Of phosphorus. And then all these other options are incorrect. Moving on to question 1.4, it says, in which one of the following compounds do covalent bonds bond occur between elementary particles, right? So this is what we're having. Which one of the following compounds do covalent bond occur, right? So we're looking for a covalent bond that occurs between elementary particles, right? So according to this, we're having an elementary particles there. It means we are going to have a covalent bond is going to be our ammonia, right? So remember, we're using the valent electrons that are found on the outer shell there, right? So then to proceed there, it says 1.5. 1.5 says, what is the percentage of hydrogen in a molecule? So we're looking for the percentage of hydrogen in a molecule of hydrogen peroxide with a molar mass of 34 grams per mole if 1 mole of the hydrogen reacts with 1 mole of oxygen, right? So now we are going to have this one there. So for 1.5 there, we're supposed to calculate the percentage composition of this one. So what are we given? We're given hydrogen peroxide. For us to be able to calculate the percentage composition, we should know the formula for hydrogen peroxide. So this is our formula for hydrogen peroxide. Then after this, now we know the mass. Then according to this, our molar mass of hydrogen peroxide should be equivalent to 34. Just to do the math there, we're going to say we're having one hydrogen, then multiplied by 2, then we're going to say plus, then oxygen is got 16, then multiplied by 2. Therefore, if we add there, we're going to get that value there, which is 34 grams per mole. Then after that, we're going to proceed. After that, we're going to proceed and say the percentage there of hydrogen. So how many hydrogens do you have there? Is 2. Is 2. So if we're having a percentage of 2 there, the number of hydrogens is 2. So we're going to say 2 all over the total mass there that we're having there, which is 34, right? So 2 over 34, then multiplied by 100. So as for us to convert to a percentage, and if we were to do our math there, we're going to get a value of 5,88%, which is our option D there. Then moving on to question 1.6 reads, if 30 grams of A reacts, so we're having 30 grams there of A reacts completely with 25 grams of reactant B, right? So which one of the following statement is correct? So we're having 30 grams of A reacts completely. So it means all of it is going to react, but it reacts with what? 25 grams of the reactant B. Which one of the following statements is correct? So it says the total mass of the product will be equal to 55 grams. So the first one there, if we add 30 plus 25, we're going to get a value of 55. So it means our correct option there, there is no need for us to proceed with these other options. Our correct option is going to be A there. If we add that mass there, 30 plus 25, we're going to get a value of what? Of 55 grams. Then proceeding to the next question, which is our 1.7. So 1.7 is there. Two identical flasks are filled with different gases at the same temperature and pressure. So we're having the same temperature and pressure there. So the temperature is the same as well as the pressure is the same. One flask contains ozone 3 and the other an unknown gas X. So the other one is unknown gas X. Then after that, the mass of the ozone gas in the flask is 0,48, right? So it means now this is our ozone, and then our ozone there has got the formula of what? Of O3. Then this one is unknown there, which is our X. Then after that, we are asked of the gas S in the flask is 0,34 grams, right? That's X. So gas X is what? So we're supposed to look for the formula that we're going to make use of so that we can find the gas X, right, in terms of these options. So according to this, now I'm going to start with the molar mass of what? Of ozone, so which is our O3. Then I'll proceed to say O3 is equivalent to, then here what are we going to have there? We're going to say oxygen has got a molar mass of 16. So if I can go there, the atomic mass of oxygen, you can see there is what? Relative atomic mass there. Right at the bottom there, you can see your oxygen is 16. Therefore, I'm going to say O multiplied by 16. So if I do my math there, I'm going to get a value of what? Of 48 grams per mole. So it's 48 grams per mole. Then after that, I'll proceed to the mass of what? The mass of ozone, right? So the mass of ozone there, they are given the mass of ozone is equivalent to 0,48 grams. There we are given there. So it's going to be 0,48 grams. After that, now I'm going to calculate the number of moles of this ozone. So I'm going to say O3 is equivalent to, how to calculate the number of moles is mass all over the molar mass, right? Therefore, if I proceed there, this is the same as what the mass that is given there is 0,48. Then I will divide by the molar mass. So the molar mass of this there, we calculated it to be 48, right? So if we can employ our calculators there, we are going to find an answer of 0,01 moles, right? So now we have got the number of moles there of what? Of our ozone. Then after that, now we are going to formulate a relationship between this. So in terms of the X that is unknown there, I'm going to say the number of moles there is equivalent to mx, right? So the unknown mass there, mx, and then all over is molar mass. Then after doing that, now I'm going to make mx the subject of the formula, the molar mass the subject of the formula. So what does that mean there? I'm going to say the mass, molar mass of this one that is unknown is going to be x all over is equivalent to mx, the mass of this one all over the N, right? Then I will proceed to calculate this one as the mx there. So the molar mass of this x there, we're given the mass of it is 0.34. So I'm going to say 0.34 all over. Then here, according to this here, they are going to react 1:1. So I'm going to use the same number of moles there, which is 0.01, right? So if we divide there, we're going to get a value of what? 34 grams per mole, right? So it's going to be 34 grams per mole, like that, right? So after that, now, if we're getting that value of 34 grams of moles, because we're using the same number of what? Of moles, then after that, if we had to look at the molar mass of this, right? So we're going to compare all these ones. So if you can start maybe with your O2 there, the molar mass of O2, what are you going to get? So I'm going to say the mass of O2m there, and then bracket O2, so is equivalent to same as 16 multiplied by 2, like that. Then for sulfur, I'm going to do the same again. Sulfur, the mass of molar mass of sulfur dioxide there is the same as what? Sulfur has got a mass of what? Of 32. Then I'm going to say multiplied by 1. Then after that, plus again oxygen, which is 16 times 2, right? Already we can see this number is too big. Then I'm going to proceed to the molar mass of H2S, which is H2S there. So if we do our math there, we'll find that hydrogen has got a mass of 1, then multiplied by 2. Then I'm going to say plus the sulfur, which is 32 times 1, right? So if we're to add there, we're going to get a value of what? Of 34 grams per mole. So it means our correct option is going to be option C, like that. Then moving on to the next question, we're done with the multiple choice questions. Now we're heading towards the structured question. So question 2.1 reads there, in the table below are different substances which use the following substances to answer the questions that follow. So we have got different substances there, then they are named A until F, then cobalt, gold, phosphorus, silicon, air, and ammonium nitrate. Then here, according to 2.1.1 says, identify the element that has a dull surface and cannot conduct electricity. So it's dull, then also it cannot conduct electricity. So our option for this one is going to be our phosphorus, so which is option C. So I can just say element C, or I can be specific in terms of which element is our C there. So this is our phosphorus, like that, right? Then to 2.1.2 says, identify one substance that is ductile, right? By ductility, we say it's a substance that can be pulled into wire, something that can be pulled into a wire. So in terms of this here, we're going to have our option, which is A, which is our cobalt, right? So I'm going to say A, or I can be specific and say this is A, our option A is a cobalt. Then 2.13 reads there, which element has got a magnetic properties, right? So which one it can be attracted by a magnet. Again, here from that list, I'm going to go with A or cobalt there. So our option A is going to be our cobalt. Then moving on to 2.1.4 says, identify the element that is a metalloid, right? So this is a more of a semi-metal, right? So a semi-metal, the only semi-metal that we are going to have there is our silicon. So come to D or silicon, like that. So this is our answer for 2.1.4. Then proceeding to 2.1.5 says, write down the chemical formula of substance for substance F, ammonium nitrate. So this is the ammonium nitrate we're asked in terms of its formula, right? So ammonium nitrate is going to be ammonium NH4, then nitrate NO3, like that, NO3. So that's how we get our 2 marks. Then moving on to 2.2 says, the base of a frying pan is made from aluminum. So the substance that is made in use of is aluminum, while the handle is made of what? Hard plastic. Then now we're asked, what benefit does the base of the pan made from aluminum have, right? So why do you think is that, right? So now Al is a metal and is a good thermal conductor. So I can say Al is a metal and and a good conductor of heat, right? Of heat, like that. So that's our answer there for the first one. So it means it also allows heat to easily pass through it. Then 2.2 says, why would the handle of the pen be made of what? Of plastic, right? So there, in terms of this one, I can say the plastic is an insulator, right? It's an insulator, right? So that's the reason why we're making use of the of the handle being what made of what of plastic. Then we are done with question 2. Now moving on to question number 3. Question number 3 is here. The grade 10 learners conducted an experiment to determine the heating curve of water by using ice cubes, right? So the heating curve. So we're focusing on the heating curve of water by using what? Ice cubes. Then the experiment was set up as shown below. So we have got these apparatus there. I think X is going to be our thermometer, and let's go through everything there. Then they're saying define the temperature, right? So define the temperature. So I would actually advise you to make use of your exam guide and try and memorize all this definition of temp, because they are very important when it comes to this, right? So temperature there is the measure of the average kinetic energy. So I'm going to say measure of the average kinetic energy of the particles, right? So particles. So it means now if the particles are having more energy, it means now they're going to have what? More kinetic energy. So if you increase temperature, kinetic energy also is going to what? To increase. Then after that, you are asked to name the apparatus X. So our X there is going to be our thermometer, right? So thermometer, which is an instrument that is used to measure our temperature. Then after that, why is it important to continuously stir the melting ice with a glass rod, right? The importance of stirring there is that so that this ice cube, so we're having this thermometer there at the top, right? So they are asking us, why should we keep stirring there in terms of our answer there, right? So now here, the reason why we're stirring here is to distribute heat is evenly. To distribute heat evenly, like that. So that's the reason why we heat we stir as this one is melting. So to distribute heat evenly in the beaker, or inside the beaker, in the beaker. So that's our reason behind. Then moving on to 3.4, it says the graph below shows the results of the experiment. So this is the graph that is obtained after we're heating and all our ice cubes there. Then they're saying name the process taking place between T1 and T2. So here T1 and T2. So we can see at the start there was an increase in temperature from -20 to a 0 there. So between T1 and T2. So it means here we're still having some ice within here. So what is happening to that ice? It is still what? Melting. So there is what we refer to as melting. Then 3.4.2 reads there, will the water particles move slower or faster between T2 and T3? So we're focusing here between T2 and T3 there. Then when compared to the movement of particles between 0 and T1, so we're comparing this one between 0 from the start and T1 there, right? So this is the part that we're looking at versus this other part there, right? So these are the two parts that we are looking at there. So now in terms of our answer, they're asking, will the particles move slower or faster? So the answer there is going to be faster, right? So remember, as we're increasing temperature, it means the average kinetic energy of the particles is going to increase then, right? So it means now particles, they are moving faster, and then the state there is becoming what? Liquid. So it means now what are we going to have? Particles have more kinetic energy. So particles in liquid, I can say liquid have more kinetic energy, like that. So that's how we attempt that question. Then moving on to 3.4.3, it says, will the potential energy between T3 and T4 increase, decrease, or remain the same, right? So they're looking for the potential energy between T3 and T4. So this is the part that they are looking for there. So this is T3 and our T4. So will the potential energy between T3 and T4 increase, decrease, or remain the same? So it means here T point there is going to increase, right? We're going to say it increases. Then can the particles be compressed between T4 and T5? Then answer yes or no, right? So yes, particles can be compressed there. They can be compressed, right? So because here, if you can look between T4 and T5, 5 there, we are more of like formulating a gas, and then this one gas can actually what be compressed there. So then moving on to question 3.4.5, it says the forces between the particles of ethanol are weaker than those in water. The forces between the forces between the particles of ethanol are weaker than those in what? In water. Then after that, will the boiling point of ethanol be greater than or less than that or than 100 degrees under the same standard conditions, right? So now we should know that the force between the particles of ethanol are weaker, right? So if they are weaker there, it means now will the boiling point of ethanol be greater than? No, it's going to be less than. So because already it says here the particles between ethanol particles, the forces of particles of ethanol, they're actually what weaker than those in what? In water. So it means now the boiling point is going to be less than 100 degrees. So under the same conditions, it means that ethanol is going to boil at a temperature that is less than 100 degrees. Then now moving on to the next question there, which is our question 4, says here question 4.1, naturally occurring oxygen consists of 3 isotopes indicated below, right? So now we need to know what an isotope is for us to be able to answer these questions, right? So the first question, so we're given an isotope here, we're given its isotope and then the percentage abundance, how much of it there is naturally what occurring, right? So now we're having isotopes of what? Oxygen, which is oxygen 16, 17, as well as what? Oxygen 18. And then here the other percentage is not given, it's given as a value of what? Of X. Then to proceed there, we are asked to define an isotope, right? So isotopes are atoms of the same element. So I can just like say atoms of the same element, atoms of the same element, okay? So atoms of the same element, having the same atomic number, having the same atomic number, allow me to use a hash there for number, atomic number, but different mass numbers, but different mass. Also allow me to use hash for number, hash there like that. So due to differences in what in the number of neutrons, right? So the difference there can also proceed and say due to diff in what? In the hash of neutrons, right? Okay, neutrons. So that's what you're having then. After that, they're asking us what percentage abundance does O18 occupy, right? So if you can look there, it's a percentage, right? So if it's a percentage, it means these suppose they are all supposed to add up to 100, right? So it means our O18 there, O18 is equivalent to, I'm going to say 100 and then subtract that 9,76 and also subtract that 0,04, right? For us to get that value there of X, right? So if we do our math there, we're going to get a value of what? According to my calculator, I'm getting a value of what? 0,2. So our answer there is going to be calculate is 0,2. So our answer is going to be 0,2. So it's a percentage. Remember, therefore I'm supposed to say 0,2 as a percentage. Then I'm going to move on to the next question, which is 4.1.3. Says here, calculate the relative atomic mass of oxygen, right? So we're looking for the relative atomic mass of oxygen, right? So in terms of this, what I'm going to do, I'm going to say relative, allow me to use this top space there. I'm going to say our relative atomic mass there. I'm going to just say rem there, relative atomic mass is equivalent to, so there I'm going to say all these percentages that we're having there, right? So we're having this for that, right? So it means here I'm going to say 99.99,76, right, multiplied by 16, right? So this one occupies 16 there, is for oxygen 16. Then I'm going to say plus, then this 17 goes with 0,04. So I'm going to say bracket then 0,04, then multiplied by 17, which is the the isotope 17 or 17. Then the last one there, I'm going to say plus 0,2. So I'm having a 0,2 of what isotope of this 18, right? Then here I'm going to say all over a total of what, of 100, right? So there, that's how we calculate our relative atomic mass. Then if we are to employ our calculators there, we should get a value of what, 99.76 times 16, then plus 0,04 times 17, then plus 0,2 by 18 all over 100, right? Yes. So it gives me a value of 16.0000. I can just say 4 like that, right? So this is what we are going to get is our final answer there. So our final answer is going to be 16.0044. Take note, it's important for you to show all this working. Don't just like write down the answer as it is. So you should show us the working that you got there until to get what, to 16.044. Then I'm going to proceed to 4.2. 4.2 says aluminum is a metal and a good conductor of electricity, which is true. Then name the type of bonding between the aluminum atom. So we're looking for the type of bonding, right? Type of bonding between the aluminum atom. So aluminum atom, that makes it a good conductor of electricity. That makes it a good conductor of electricity. So now it means here what we're going to have there, the type of bonding there is referred to as a metallic bond. It's a metallic bond. So this type of bond enables aluminum to be a good conductor of what? Of electricity there. Then moving on to 4.2.2, saying state and explain, right? So just not only state, there's a capital letter and, so that to see that we should do another thing. There is an emphasis. So state and explain another one property of aluminum that can be attributed to the type of the bond identified, right? So in terms of this 4.2, I can say this aluminum is that ductile, right? So ductile, I can say it's ductile, right? What do you refer by ductility is that it is the ability of it being pulled into what? Into wires. It can be stretched into a wire, it can be pulled into a wire. So that's the other property. And then also the other property is that it's malleable, right? So malleable. So what does this mean? It means it can be hammered into any shape. So that's our answer there. It can be hammered into any shape. So then after that, aluminum reacts with nitrogen according to the following reaction equation. So what we have there, we're going to say Al plus N2 to give us Al N there, right? So name the product that forms. So the product that forms there, you can see is ALN, right? So now we're asked to name the product that is actually formed. So this one is going to be our aluminium, then nitrite. So that's our answer there. So if we are to write this one ALN there, you are going to forfeit your marks because now we needed the name there, right? So then after that, they're saying use a Lewis diagram. So we're supposed to draw a Lewis diagram there to show how the product is formed. This product, which is your AL, in there, right? So in terms of this, I'll start with the reaction of Al there, right? So if I can just like check at my periodic table there, Al, so you'll find that we're having our LAL there, which is group number 3. So what does that mean? It means it has got 3 electrons on its outer shell, right? So I'm going to have my Al there, then after that 3 electrons on the outer shell like that. Then after that, I'm going to add, what did we add to N2, right? So the nitrogen there. So let's look at nitrogen. Where can we find nitrogen? So nitrogen is in group number 5 there, right? So what does that mean? It has got 5 electrons on the outer shell, right? I'm going to say N there. Allow me to use X, 1, 2, 3, 4, and then what? 5. So it's 5 electrons on the outer shell, right? Then how are they going to formulate the product there? I'm going to say L3 plus. Why is that so? Is because all these electrons are going to be what? To be given to N there, right? Then after that, now what also am I going to have there? I'm going to have something like the 1 for nitrogen is now going to look like this. I'm going to say N there. So this is what you're having there originally. something like that, something like that. So if you can allow me to use maybe a different color to show where these other electrons now are attached. So these were the electrons for our aluminum, from our aluminum there, right? The red ones. Then after that, now this is what we are having as our final product. So this is how it's supposed to look like. Then after that, I'm going to say 3 negative to show that it accepted 3 electrons. Then this one is a positive 3 plus that to show that it gave out, it donated how many electrons? 3 electrons. So remember also what is transferred are the number of what are the electrons. Sorry, protons are not transferred. Then moving on to question number 5. So question number 5 there, what are we given? We're given a graph. So a graph says here, the question reads, the graph below shows the first ionization energies, right? So I'm referring to ionization energies of elements of period 3. So we're focusing on period 3 in the periodic table, right? So it's only period 3, right? Then here we're having the value of the first ionization energies there. Then after that in kilojoules per mole, then here we've got the different elements which are in period 3 there, right? So remember, how do you identify a period, right? So a period is across, right? So across like this, going down to the left, or left to the right, or right to the left. Then your group is the one that goes way downwards like that, right? So the vertical ones are referred to as the groups. Then the one that goes horizontal, they are referred to as our periods, right? So we're only focusing on period number 3. Then after that, we are asked to define the term first or the term ionization energy, right? So it's defined as the minimum energy. So the minimum energy, the minimum energy. So it's defined as the minimum energy. I'm going to say per mole, the minimum energy per mole required to remove an electron, an electron from an atom, in the gaseous phase, So that's what we're having there in terms of that. Then now they're saying 5.2, describe the general trends. Right? So the general trend in the first ionization energies from sodium to argon, right? So sodium to argon, right? So this is the sodium there that we're having, and then the argon there, right? So in terms of this, now what's the trend, right? So it means here, if we can look at this, the ionization energies, beside dropping there, here, and this part where there are slight drops, right? But the general trend is that it's increasing, right? So we're going to say increasing, right? So there is an increased ionization energy, increases from, so ionization energy, first ionization energy, I'm going to say increases from where they said we should start from sodium. So I'm going to say increases from Na to our argon there, which is our Ar. Then after that, now 5.3 asks us to explain the differences in the first ionization energy of magnesium and chlorine, right? So now let's look at the first ionization energies of magnesium and chlorine, right? So if I can erase that part there, what you're going to have there is the first ionization energy there. Just try to minimize a little bit. So the first ionization energy that you're having there is going to look like for magnesium, we are supposed to explain the first energy of magnesium and chlorine, right? So this is our Mg there. So I'm going to circle it there, then also erase maybe all these other ones. And then also we're supposed to look at what? A chlorine. Yes, a chlorine, right? So this is what you're having there, Cl there. So this is chlorine there. So we are supposed to explain the differences, right? So for the differences there, we are going to say, start with, maybe if we are to start with so magnesium there. So in terms of magnesium, where do we find our magnesium, right? So in which group is magnesium and in which group is our chlorine, right? So I'm going to start maybe with let's start with chlorine, right? So now I'm going to say your chlorine there, which is your Cl. Here's a a greater first ionization energy as a greater first ionization energy, right? So that's our chlorine there, right? You can see there is at the top, so around above 1.2. Then the one for magnesium can see is in between 600 and 800, so I can assume it's roughly around 700 there, right? Then after that, I'm going to proceed again and say chlorine and magnesium have the same hash of what energy levels, right? So magnesium and chlorine, Mg and Cl, right, have the same number of energy levels, right? So energy levels there, right? So energy levels there. So it means here, remember, they are within the same period, right? So the energy levels there, we're going to say they are the same. So energy levels, but in terms of chlorine, but Cl has more electrons, right? So he has got more electrons than I'm going to say than Mg, right, which is our magnesium there, right? Then after that, now it says therefore chlorine in nucleus. So I'm going to say the Cl nucleus is going to pull all these electrons to itself, right? So pulls the valence electrons. It's going to say pulls the valence electrons. So the ones on the outer shell, right? So valence electrons, it pulls them electrons more strongly than so we're talking about the Mg nucleus, the nucleus of the Mg, right? So because of that, now that's why we're having those differences in what in the first ionization energies, right? So that was our 5.3. Then moving on to 5.4. 5.4 says, how will the second ionization energy from sodium compare to the first ionization energy? Choose from greater than, equal to, or less than. Then we're supposed to explain our answer in terms of our choice there. So for this one here, we're going to say it's going to be greater than. It's going to be greater than, right? So I'm going to start by saying greater than. Then after that, I'm going to explain. So I'm going to say greater than. Then after that, let's explain. So the reason behind is that the sodium ion has got a completely filled outermost energy level. So I'm going to say sodium. The reason behind is that sodium ion there, sodium ion. So you can see it's now an ion because it already that outer part has been taken out, right? So I'm going to say sodium ion is a completely completely filled outermost energy level. So take note there. What are we going to have there? So sodium is in group number 1. So it's actually ready to give out its electron there, the outer one, right? Found on the outer shell. So it means basically what I'm trying to say here is that it formulas something like an NH plus, right? Then after having that NH plus, now we're going to proceed to say Na energy level, then energy level, and therefore does not want, and therefore not want does not want it to lose any more electrons, to lose any more electrons. So electrons. So it achieves something that looks like more of what? A stable octet, right? So if it's achieved a stable octet there, so it's going to be difficult for it to lose more electrons, right? Therefore, now that's why the energy is going to be what? To be greater than. So it's in a condition where it's actually stable. So you taking out that electron, it makes it what? Unstable. So it's going to try and like use, for you to take it out, you are going to require what? More energy, right? So to force that one to be taken away, right? Uh, so now I'm going to say the second electron as a conclusion the second electron, to be removed, second electron to be removed. What happens to it? So the second electron to be removed is closer to the nucleus, is now closer to the nucleus, right? So if it's closer to the nucleus, it means now it's strongly attracted to the nucleus, right? So and will experience, I'm going to say, and will experience a greater attraction, with the nucleus, with the nucleus, like that, right? So then after that, now what does that mean here? More energy will be needed, right? So I'm going to conclude by saying more energy will be needed to overcome that force, to overcome that force there. So that's how we conclude our question number 5. Then moving on to the next question, which is our question number 6. Right, so 6.1 reads there. Classify the following as physical or chemical change, right? So there are two there, physical or chemical change, right? So please, whenever you encounter such questions, do not leave them blank. So I'm going to say classify the following as a physical or a chemical change, right? So in terms of this one, the first one, it says the iron metal is melted, right? So it has a metal, then iron metal there is melted, right? So if it actually melts there, what does that mean there? It means here it's going to be remain as a physical. So I'm going to say it's a physical change. Why is that so? Because here there is just what a change in state, right? So here is a phase change, right? So I'm going to say the reason behind is a phase change, right? So that's our answer there. There is a change in phase, right? So now the chemical composition of this metal remains the same. Can be also another reason there, right? Then gray hair is dyed to a red color. So now someone has what? Black hair, then they actually turn blonde. So same applies here. They're having gray hair that is dyed to a red color. So is this going to be a physical or a chemical change? In terms of this one, it's going to be a physical change there, right? So I'm going to repeat again, say a physical change, right? So the properties of the hair are still the properties of what? Of the hair there. So the properties haven't what? Changed. So the composition remains what? The same as what? As hair. What happened there? Yes, I know we understand we are using chemicals. So someone might be tempted to say it's chemicals since we are using what? Chemicals to dye your hair. But now the property of the hair remains what? The same. Then here, 6.1.3, a car rusts, right? So here, what is going to happen there? There's going to be a chemical change. So this one is going to be a chemical change, like that. Okay, so at the top, let me just say change again. Then after that, now why is it a chemical change? Because the properties of the metal there, they are going to what? To be changed there. Then 6.2 is there, the balanced equation for the reaction of 2BNO3 solid there to give us that 2PBO, then 4NO2 and O2 gas, right? Then now what type of reaction is shown above? In terms of 6.2.1, so you can see here there was more of like a breakdown of this reactant there to formulate more of what? Of products, right? So if it's something like that, automatically know the type of reaction is referred to as what? A decomposition reaction, right? So it's composition reaction because there was a breakdown of the original what? Reactant to formulate what? More of our products. Then 6.2.2 says by use of calculations, right? So we're supposed to use a calculation, prove that the law of conservation of mass is true for this reaction, right? So law of conservation of what? Of mass is true. So the law of conservation, yes, is that whatever we're having on our left side should be equal to what we're having on our right hand side, right? So now these masses should be equal from our left to our right there. So to work this one out there, I'm going to like make use of a space. Try and find some space. Just a second to find some space. Okay, so now we're going to use this other page for us to do our calculations there, right? So according to this equation there, we're having a 2 PB. So let me just like quickly copy this equation there, 2 PB, then NO3 to NO3 to NO3 then 2. So to formulate our product there, so our products are 2 PbO, 2 PbO, 2 PbO like that, and then after that plus 4NO2 plus 4NO2 plus 4NO2, then to also give us our oxygen, which is a gas, so plus our O2, right? So in terms of this now, what you're going to do is to find the molar masses of each, right? So now in terms of this, I'm going to start on my left hand side. So I'm having a 2, right? So this 2, it means it affects everything there, right? So 2 multiplied by our lead there, which is 2 07. So if we are looking for PP there, this is our PP, which is 207. Therefore, I'm going to say bracket there. Maybe use a square bracket there. Then I'm going to say 207. So it's going to be 2 multiplied by 207 there. Then I'm going to say here lead is only one of it, right? So I can multiply by 1 and proceed, right? So let me just put it in bracket, and then so also plus, then our nitrate there, you can see, is also going to be how many? Our nitrogen there is going to be N multiplied by 2, right? So if we are to look at our nitrogen there, you'll see that it has got a mass of what? Of our 14 there. So we're going to use 14 there for that one there. I'm going to say 14 multiplied by 2, right? So it's going to be 2 multiplied by 14 like that. And then I'm also going to add our oxygen. So according to this, our oxygen there, our oxygen has got a mass of what? Of 16 there. So I'm going to say the relative atomic mass for oxygen is 16. Then we're going to say 16, then multiply our 16 by what? By 3 there, right? So this is 16 multiplied by what? By 3 there. So 16 multiplied by 3, 16 times 3 like that, right? So now in terms of this, if we were to add there, so I'm going to say is equivalent to on the other end, right? I'm going to say is equivalent to on the other end is equivalent to square bracket, then 2 PbO, then I'm going to say 2 again here. So it's going to be 2 multiplied by 207. I'm going to say 207, and then plus our oxygen, which is 16. Then also add there 4 multiplied by, so it's going to be 4 multiplied by, I can put this into square bracket there. Nitrogen, we already know is 14, right? I'm going to say 14 plus our 16 there, our plus 16 by 2, right? So it's going to be plus 16. I'm going to say bracket there multiplied by what? By 2 there. Then plus again there, the last one, which is going to be our oxygen, right? So it's going to be 16 times 2, right? So if we are to do our math, then I'm going to say here on my left hand side, I'm supposed to get something like this, 207 bracket, I'm going to say 207, then plus my 124 plus 124, then I'm going to say is equivalent to on my right hand side there, according to my math, I got a value of what? 446 is equivalent to 446. Then I'm going to add there plus our 184 plus our 184 plus our 184 plus our 184, then I'm going to say plus our 32 there, right? So plus our 32. So this is what you're going to get. So now if you equate these two, you're going to get a value of what? 662. 662 is equivalent to on this other end also 662. So that's how we attempt that question there, which is question 6.2.2. Then to proceed to the next question, which is our 6.2.3 is then when 6.62 grams of lead nitrate, which is your PbNO 32, is heated, 4.46 grams of solid is produced. what is the mass of the gas that will be produced there, right? So in terms of 6,2.3, so now we're looking for the mass, right? So it means now we started with this, which is 6,62. So I'm going to take that value there, 6,62, and then now is heated. 4,46 grams of the solid is produced. It means the other one actually evaporated, right? So into a gas, right? What mass of this gas there, right? The one that actually like went out, right? So it's going to subtract then. We're supposed to subtract there. How many? We're going to subtract that value, which is minus 4,46, right? So if we are to do our math there, we're supposed to get an answer of 2,16 grams. So 2,16 grams. Then we are done with that question. Moving on to 6,3, it says balance the following reaction equation, right? So we're having that there. So we're supposed to balance this equation there, right? So if we're to look at our nitrogen, what are we having? Our NH3 gas plus our O2 gas to give us our NO2 gas, and then plus our H2O, right? So in terms of our hydrogens on the left there, we're having 3. Then on my right, I'm only having 2 of them, right? So now if I'm having 2 of them, what does that mean? Now I'm supposed to try and balance them, right? So now if I can start with my hydrogens, if I'm having 3, so if I can just like make it a round figure, maybe I'm going to say if I multiply everything on this side here by NH3 there, then I'm going to say plus, if I use a coefficient of 4, then after that I'm going to say plus my O2. For now I'll leave it like that. Then after that I'm also going to proceed and say NO, then leave it like that. Then the last one is going to be what? H2O, right? So if I place my coefficient of 4 there, what is going to happen on this other end? So this is my hydrogen. So it means now 4 times 3, now I'm having a total of 12 hydrogens, and here I'm still having 2. So it means now I should multiply with the coefficient of what? Of 6. Then after having a 6, then it means now I'm going to go back and say again, my nitrogen here I'm having 4, on this side I'm only having 1. So what should I do? There I'm supposed to also multiply by a coefficient of what? Of 4. Then having a coefficient of 4, now we are left with oxygen, right? So look at oxygen here. By having 2 on my left, here on my right is going to be 4 plus 6, which is a total of what? Of 10. So to make it 10 there, I'm supposed to multiply with the coefficient of what? Of 5. So this is our final balanced equation there. Moving on to question number 7. So question number 7 says here, calculate the concentration of a solution prepared by dissolving 5.85, so 5.85 grams of sodium chloride, right? So having sodium chloride in enough water to make 500 cubic centimeters of the solution, right? So calculate the concentration. So we're looking for concentration, right? So in terms of this, we're going to say your concentration there is equivalent to, you see, is equivalent to concentration of sodium chloride there. So NaCl is equivalent to the number of moles all over the volume, right? But looking at this now, do we have the number of moles there? We don't, right? So, but what are we given there? We're given the information about what? Sodium chloride there. So it means now I'm going to use the number of moles of what? Of sodium chloride, right? So I'll start with this formula. Number of moles of what? Sodium chloride there is equivalent there to M all over M. Please make use of your data sheet. Be wise in terms of that. Just copy the formula as it is, right? So the mass that is given there is 5,85. So it's 5,85 all over. Then the molar mass of this one there for sodium chloride. So if you're going to say your sodium there is going to be 23 plus 35.5. So I'm going to get a value of what? 58,5 there, right? Then after that, it means now if I to do my math there, according to my calculator, it gives me a value of what? 5,85 divided by 58,5. I'm getting a value of 0,1. So remember, these are the moles, right? So I'm going to get that value. Then now I can take those moles and then substitute them into this equation here. So I'm going to say your concentration. I'm going to proceed and say the concentration there is equivalent to number of moles. Then I'm going to plug that 0,1, which I got from this side, right? So it's 0,1, then all over the volume, right? So if you can look here, we are given in cubic centimeters, right? So for us to convert to dm cube, they were supposed to divide by 1,000. So if we divide that one by 1,000, we're going to get a value of what? 0,5. So it's all over 0,5. Then after that 0,1, divided by 0.5. Our answer is 0.2. Then the units of measurement there, I'm going to say mole per dm cubed. Then we're done with question 7.1. Then moving on to 7.2, it says explain the concept of water of crystallization and give a formula, water of crystallization, and give the formula of a common hydrated what salt, right? Hydrated, it means the one that contains what water. Then I'm going to explain the concept there of water of crystallization. So this is question 7.2. So I'm going to say 7.2 there. So water of crystallization refers to water of crystallization refers to the water molecules. So to the water molecules, okay, that are I can say that are stoichiometrically bound. Stoichiometrically bound, right? Okay, so I can say bound or bonded. Okay, bonded with within, I can say water of crystallization refers to the water molecules that are stoichiometrically bonded with the crystal structure, with the crystal structure of a salt, of a salt, right? So here we can have our zinc sulfate as an example. Zinc sulfate, then I'm going to say dot there, maybe 5H2O, right? We can also you make use of our copper sulfate as an example, dot then 5H2O, right? So this is water that is being stoichiometrically bound, right? So they're saying common hydrated salt, so that's what we're having there. You can choose either of these between these two as your what is a common salt there that is stoichiometrically bound or under water of what crystallization. Then moving on to question 7.3 says a learner has hits 5 grams of a hydrated salt until all the water of crystallization has evaporated, right? And then leaving 3 grams of the anhydrous salt. So anhydrous salts without water. Determine the percentage of water of crystallization. So we're looking for the percentage of the water of crystallization in the hydrated salt, right? So now 7.3, what we're going to do there, it says for us to calculate the in terms of determine the percentage. Okay, so I think here what they really needed maybe was to determine the mass, right? So I'm going to say the mass of the water. Let me start by saying mass of the water is equivalent to, so we started with 5 grams, right? Then after that, what happened? They evaporated until the water evaporated, and then leaving how many grams? 3 grams. So I'm going to say 5 minus 3. What am I going to get? I'm going to get a value of what? Of 2 grams, right? So maybe as a percentage, what you're supposed to do there, so percentage of the water, I'm going to take that value and then proceed to say percentage of the water. So allow me to use this space there underneath. Okay, let me just maybe use a different color. Then after that, I'm going to say the percentage of what? Of H2O. So is equivalent to mass of the water. I'm going to say mass of what? Of H2O there all over the mass of the hydrated salt, right? Mass of hydrated salt, right? So then after that now, for us to work it out there, I'm going to proceed and say percentage of H2O is equivalent to, then what do we have there? So it's 2 all over 5 multiplied by 100, right? So if we were to do our math there, we're going to get a value of what? So this is equivalent to a value of 40%, right? So 40% of this one is the one that is the water of crystallization in the what? In the hydrated salt. Then moving on to question number 8 there, which is our final question. Question 8 is there. So there are several steps in the production of fertilizers. So in the third step, nitrogen dioxide, so they're having nitrogen dioxide in the third step is absorbed by water to produce nitric acid. So nitric acid and ammonia, so these two and ammonia can react together in an acid-base process or acid-base process to form the salt. Then ammonium nitrate, which is soluble in what? In water. Then they were asked to define this the equation there, so which is a third step, first, second, and or then define the term 1 mole. So how do you define a mole there? Yes, I know this one you got it correct. So the mole there is the number of particles of a substance. I can say the number of particles, the number of particles of a substance, the number of particles of a substance that is the same as they are atoms in 12 grams carbon 12, right? Like that. Then after that, give the scientific name of nitric acid, right? So we're looking for the scientific name of what? Of nitric acid, right? So it means here, what we have there is our nitric acid. We're going to have something that is referred to as hydrogen nitrate, right? So it's going to be hydrogen, the nitrate, like that. So this is what you're going to have. Then endpoint 3 there, it says calculate the molecular mass of ammonium nitrate, right? So ammonium nitrate, then we are looking for the molecular mass, right? So I'm going to say the molecular mass there is going to be N, then M there is, it means it's NH4, then according to that equation there is NO3, right? NH4NO3, right? So this is the one that you're having then after that I'm going to say this is equivalent to, so your nitrogen there is 14 multiplied by 1, then plus, it's just a matter of you using your periodic table there, 1 multiplied by 4, because we have got hydrogens, 4 hydrogens. Then of course to proceed again, as I'm going to say nitrogen again, we've got only one of each, so it's going to be 14 multiplied by 1, then also 8 plus, then the final one is oxygen, which is 16, and then we're having 3 of them, right? So if we are to do our math there, we are going to get a value of what? Of 80. So it's going to be 80. Then units of measurement there should be grams per mole, right? So this is how we get our molar mass. So this is question 8.3.1. Then moving on to 8.3.2. So 8.3.2 says calculate the number of moles, right? So we're looking for the number of moles of ammonium nitrate if 15 grams of it was used, right? So now the number of moles for this one, calculate the number of moles of ammonium nitrate, right? So what I'm going to do here is to calculate the number of moles. So by formula, you know the number of moles. I'm going to say NH4NO3. Please just copy the formula as it is from our data sheet. Then after that, you can substitute with what? With the values. So the mass that is given there is 15, and already you have calculated our molar mass there to be what? To be 80. Then if I say 15 divided by 80, this one gives me a value of what? Let me just erase there. So according to my calculator, I'm getting a value of 0, okay, I can say 0.19 moles there. So I'm done with question 8.3.2. Then moving on to question 8.3.3 there. So I'm going to have that one there, division then. Then after that, I will proceed to say what do we have there? It says the volume of 12 grams of nitrogen at STP, right? So this is standard temperature and pressure. So what you're going to have there is that I'm going to start by the molar mass of NO there, right? So I'm going to say molar mass of NO is equivalent to, so nitrogen there is 14 multiplied by 1, then I'm going to say plus again, your oxygen there is, how many oxygens do we have? We only have 1, 16 by 1, right? So if we're to do our math, there is more of like 16 plus 14, therefore we're going to get a value of what? 30 grams per mole, right? Then after getting our value of 30 grams per mole, we can now proceed and calculate the number of moles of what are our NO there, right? So the number of moles of our nitrogen oxide is equivalent to, by formula, the number of moles is calculated by M all over M. So to proceed there, the mass that is given there is 12 grams. We're given this mass there, which is, 12 grams of nitrogen. Therefore, I'm going to say 12 all over the molar mass there. We already calculated the molar mass, which is equivalent to 30. Then if we do the math, 12 divided by 30 there, we're going to get a value of what? 0.4 moles. According to my calculator, I got a value of 0.4 moles, right? So let me just continue with that division line there, like that, right? Then after that, now let's proceed. Then after that, now I'm going to say, right, so the number of moles, right, according to your data sheet there, if you can just maybe have a look at the data sheet, what you're going to have there is our formula. So we can say the formula there is equivalent to, N is equivalent to V all over Vm, right? So N is equivalent to V all over Vm, right? So now what are we looking for? We're looking for the number of moles for the volume of this NO, right? Then after that, I can just maybe do it like this. So as a continuation, I can just say N bracket NO is equivalent to that, right? So now we already have the number of moles, right? So it means here is going to be 0.4 is equivalent to the volume that we're looking for all over the VM. So the VM there, because it's under standard conditions, right? So temperature and pressure, STP. So we're going to use 22.4. Therefore, our V is equivalent to a value of what? So if you multiply that one there, we are going to get a value of what? 8,0.4 multiplied by 22.4. We're going to get a value of what? 8,96. Then the units of measurement, we're going to say dm cubed, because this is our volume, right? Then moving on there to the next part, which is our last question here, according to this, which is 8.3.4, says nitrogen atoms present in 2 moles of ammonium nitrate, right? So this one is going to be something like this. So we're going to proceed and say the number of moles there, right? So the number of moles there is equivalent to, so I'm going to say N is equivalent to Na all over N, right? So Na all over the N there, right? Then after that, I'm going to say the number of moles that we're having there is 2. Then after that, it says here, these are the number of moles we're given already, is 2, then is equivalent to, then after that now, the constant there of Na, right? So it's going to be 6,02 times 10 exponent 23 there, right? We find it on our data sheet, right? All over N, right? So now if we were to do our math there, our N is equivalent to N all over Na. No. Let me just restart on this one here. Let me just redo this one there. Let me redo this one there. So let's just maybe refer to our data sheet real quick there. So we're looking for this formula that says N is equivalent to, so it's supposed to be N is equivalent to N all over Na there, right? So we're going to say N is equivalent to N is equivalent to N all over Na there, right? So this is our correct formula there, right? Then to substitute with the values there, we're going to say 2 is equivalent to your N, right? So your N there, you don't know it, then the constant there is going to be 6,02 times 10 exponent 23. Therefore, your N, to conclude there, you're going to say your N. So if you cross multiply 2 times 6.02 times 10 exponent 23, we are going to get a value of 2,41 times 10 exponent 24. Then now I'm going to say atoms, right? So these are the atoms of of nitrogen that we're looking for. So now with that being said, we're done with our paper. Thank you for watching.